Hello everyone, and in today's lesson we want to look at how we can use the method of characteristics equation to solve a quasi-linear PDE. How we can use the method of characteristics equation to solve a quasi-linear PDE. If you haven't yet subscribed to the channel, kindly hit on the subscribe button for me. So let's look at this particular example on the board. We want to solve the equation x(u(x) plus y(u(y) is equal to u squared minus 1 for the real s greater than 0 with this initial condition or auxiliary condition. So from this equation, we can see that we have a dependent variable multiply its partial derivative, a dependent variable multiply its partial derivative with respect to y and then with respect to x. So when you have a PDE of this variable form or of that variable form, then we can say that that PDE is a quasi-linear PDE. So how do we solve a quasi-linear PDE using the method of characteristics? In fact, we are going to follow the same steps that we used when we were looking at the semi-linear PDEs and then the linear PDEs in our previous lesson. So in doing that, we are just going to identify our A, our B, and then our F from the equation given, and then we form the characteristics equation from that. So let's do that. So from the equation, our A is the coefficient of what ux, and that is what x u, and then our b is the coefficient of uy, and that is what y u, and then our f is the function on the right hand side of the equal sign, and that is what u squared minus what 1. We write down our characteristics equation. So we know that the characteristics equation is given as dx all over a is equal to dy all over b is equal to what du all over what f. So this characteristics equation is going to transform or convert this partial differential equation into an ordinary differential equation. And once we have that, we can use any method that we know in solving ordinary differential equation to solve it. So let's plug in this. We are going to have our dx all over a. Our a is what? X ux, and this is equal to dy all over b, and b is what? Y u, and then we have du all over what? U squared minus 1. Now once we have the, what we are going to do is to, so we know that when our f is not equal to 0, we are going to form two equations from the characteristics equation. That is going to give us two solutions. So we are going to form two equations to give us two solutions from the characteristics equation because our f is not equal to 0. So with this, we are going to pair this with that, and once we are done, we pair the u with any one of them. Very, very easy and then interesting. So we are going to start with this. We are going to pair the x and then what? The y to give us our first equation. So we have our first equation. So we have dx all over xu is equal to dy all over y u. Now we know that we have dx and then x, we have dy and then y. So we can separate the variables if we are able to massage this equation. So we know that when we multiply both sides of the equation by u, this u go, this u also go. So we can do that. So we are going to multiply both sides of the equation by u. So we have u times dx all over what? Xu is equal to what? D is equal to u times dy all over yu. So from here we can see that our u here will cancel the u here, and then this u also cancel this u. So we are left with what? We are left with dx all over x is equal to what? Dy all over what? Y. So from this, you can see that we have separated the variables and we can just integrate. So we are going to take the integral of that, and then we take the integral of that. So when we integrate the x over x, we are going to get what? Ln of what? X. then we have plus, we add our constant of integration, C1. And then when we integrate the y over y, we're also getting what? Ln of what? Y. Very, very interesting. So what we are going to do is to apply our basic knowledge in logarithm. Since we have ln and ln, we can pick one of the lns, and then we multiply the argument. So we have x C1 is equal to ln of what? Y. Now we are interested in making C the subject of the equation, or C1 the subject. So let's take the e on either side of the equal sign so that this e will cancel the ln, this will cancel the ln. We are left with what? X C1 is equal to what? Y. We are interested in making C1 the subject, so we divide both sides by x, both sides by x, this will cancel this. So from here, you can say that our C1 is equal to what? Y all over x. Very, very easy and then simple. So this is our first solution. We have our first solution. Now once we are done with our first solution, we are going to move on to our second equation that is going to give us our second solution. So with that, we are going to pair the u with any one of them. But the one that you are pairing, it should be convenient and then easy to work with. So looking at this, you can see that we can pair the u with this. It will work. We can also pair the u with what? This. It will also work. So let's pair the u with the x. So this is our second equation. So we have dx all over xu is equal to du all over what? U squared minus 1. So looking at this, we have dx over x. We also have du over u. But we have dx on xu. So it means you have to get rid of this u so that we can have dx over x and then du over this, so that we can just integrate, separate the variables and then integrate if it is possible. So let's multiply both sides of the equation by u to get rid of this u. So we have u multiplying the x all over xu, and then we have u multiplying what? Du all over u squared minus 1. So from here, this u cancel this u, and then we have that. So we are left with the x all over x is equal to what? U du all over u squared minus 1. So from here, you can see that we've separated the variable into x and then what? U. So we can integrate straight away. When we integrate the x over x, we are going to get what? Ln of what? X. Since we are having ln, let's take the ln on the constant as well. And then when we integrate u du all over u squared minus 1. Now for this integration to become very easy for us, let's apply some small algebra to it. Now realize that when we differentiate u squared minus 1, we are getting what? 2u. So u, and then we have what? U squared minus 1. So this is going to give us a function and its derivative, and this becomes easy for us to integrate. So what we are going to do is that we are just going to make the numerator to be what? 2u by multiplying the top and down by what? 2. So when we do that, we've done nothing to the function because this will cancel. We are having 1, a factor of 1. So we can write this as the integral of 2u all over u squared minus 1, and then we have the u. So we are going to bring it in front so that we are going to have 1 half. So we have 1 over 2. Now when we integrate 2u du all over u squared minus 1, we have a function and its derivative. So we are going to have ln of that function, u squared minus 1. Very, very interesting. So with this, we are going to have 1 all over 2 ln u squared minus 1. So from here, applying our basic knowledge in logarithm, since we have ln and ln, we can decide to take one of the ln, and then since we multiply the argument, we have x multiplying c2, and then we have 1 over 2 ln u squared minus 1. Now let's clear the half or the fraction from the equation by multiplying through by 2. So we are going to have 2 multiplying ln x c2 is equal to ln u squared minus 1. So we can write this as ln of what? sc2 all squared is equal to what? Ln u squared minus 1. Now let's clear the ln away from the equation by taking the e on either side of the equal sign so that this will cancel the lns. And at the end, we are left with what? sc2 all squared is equal to what? U squared minus 1. Now we are interested in making c2 the subject, which is going to give us the second solution. So we can expand this and write it as s squared c2 squared is equal to u squared minus 1. We are interested in making c2 the subject, so we have c2 squared is equal to u squared minus 1 all over what? S squared. Very, very interesting. Let's continue from where? Let's continue from here. Since c2 is a constant squared is still going to give us what? A constant. So we are going to write c2 all squared as what? c2, because a constant squared will give us a constant. So we are going to have our c2 is equal to what? U squared minus 1 all over what? S squared. So this is our second solution. This is what? Our second solution. Now, since we are having 2 solutions, C2 and C1, one become a function of the other. So it is either C2 become a function of C1 or C1 becomes a function of C2. Since we are having the U, the dependent variable U in C2, let's make C2 to become a function of C1. So C2 we have U squared minus 1 all over X is equal to a function of C1 we have Y all over what? X. So once we have this, let's try to see if you can make U squared the subject. So we are going to multiply through by S squared. So we have U squared minus 1 is equal to a function of Y all over X. And then we have a multiply by what? S squared. So we can bring 1 to the right hand side. So we have our U squared is equal to a function of Y all over X multiplying S squared plus 1. So this becomes our general solution. We can decide to take the square root so that we have our U at X, comma Y is equal to the square root of a function of Y all over X multiplying S squared plus 1. So this becomes our general solution. It becomes what? Our general solution. Very, very easy and then simple. So we realize that we're given an initial condition. So this is the initial condition. So we have to look for the particular solution. So let's write our general solution. We have U at X, comma Y is equal to what? The square root of So with the initial condition, what it means that wherever you see X, we plug in what? X, and then wherever we see Y, we plug in what? X squared. Very, very interesting. So from the general solution, we have U at X, our Y is what? S squared. So we have S squared is equal to what? Square root of a function, our Y is what? S squared all over what? Our X is still X, and then we have S squared plus what? 1. So we have our U at X, comma S squared is equal to, this will give us what? X multiplying S squared plus 1. So we said that the initial condition U at X S squared is equal to what? S cubed. So we are going to write it as U at X S squared is equal to what? S cubed. Now since we have U at X S squared, U at S S squared, since they are equal, we can equate this one as well. If you have two equations, let's say P is equal to 0 and then Q is also equal to 0, then we can say that P is equal to Q. So we are going to apply the same concept here. Since this is equal to that, then it means that this is also equal to that. So we are going to have our square root of f at x multiplying s squared plus 1 is equal to what? S cubed. Now let's do away with the radical sign by squaring both sides of the equal sign, so that this will cancel this. So we have our f at x s squared plus 1 is equal to x raised to the power 6. Now we are interested in making f at x the subject, so let's bring this to the right hand side. So we have f at x s squared is equal to x power 6 and then minus 1. Let's divide both sides by what? S squared. So we have our f at x is equal to x power 6 minus 1 all over. So at this point, what we are going to do is that we are going to find out what happened to x that gives us what? This. So we are going to let any variable at all, let's say p, to represent what? X. So we are letting p to represent what? X. So it means that wherever we see x in this equation, we are going to represent it with what? P. So we are going to have f at p is equal to what? P power 6 minus 1 all over what? P squared. So at this point, we are going to go back to the general solution. We are going to go back to the general solution, which is this part. And then wherever we see f at, so we find the function f. And then what is in the bracket, we are going to represent it with what? P. Or we are going to substitute what is in the function here in place of what? P. So we are going to have f at y over x is equal to, we are saying that p is equal to what? Y over x. So we are going to have y all over x raised to the power 6 minus 1 all over what? Y over x, and all of this is what? Squared. So from here we can do some small algebra. We can write this as all over what? X raised to the power 6 times this, we can write it as what? S squared all over what? Y squared. So that this will cancel. So it means we can write the whole of this as y power 6 minus x power 6 all over x raised to the power 4 multiplying y raised to the power 2. This one is 2 raised to the power 2. So finally we have our f at y over x is equal to y power 6 minus x power 6. Then we have all over x raised to the power 4, y raised to the power 2. So it means that wherever we see f at y over x in the general solution, we are to plug in this. Wherever we see f at y over x in the general solution, we plug in this. So we are going to have our particular solution to be u at x comma y is equal to the square root of. So we said that wherever we see f at y over x, we are plugging the whole of this. So we have y power 6 minus x power 6 all over x power 4 y power 2 multiplying what? S squared plus what? 1. So from here you can see that s squared will cancel s squared here. So we'll be left with the square root of y power 6 minus x power 6 all over s squared y squared plus 1. And this becomes the particular solution of the question there. Very, very easy and then simple. So we have the particular solution. Very, very easy and then simple. We are going to look at another example. So we want to solve the equation x u u x plus y u u y is equal to s squared plus y squared. with the initial condition this. So we have to find the general solution, and then once we are done with the general solution, we find the particular solution using the auxiliary condition given. So looking at this PD, realize that we have the dependent variable u, or the unknown function u, multiply its partial derivative with respect to x. We have the dependent variable u multiply its partial derivative with respect to y. So you can see that this was a quasi-linear PD, and we are going to solve using the method of characteristics. We are going to follow the same approach that we used when we were looking at the earlier example. So first, we are going to identify our a and b, and then f from the equation given. So our a is the coefficient of ux, and that is what? Xu. And then our b is the coefficient of what? Uy, that is what? Yu. And then our f is what? S squared plus what? Y squared. So once we have this, we form the characteristics equation, and we know that the characteristics equation is given as what? Dx all over a. So our a is what? Xu. And then we have dy all over b. Our b is what? Yu. And then we have our du is over what? F. Our f is what? S squared plus what? Y squared. Very, very easy and then simple. Now I realize that our f is not equal to 0, so we are going to form two equations from this characteristics equation. That is going to give us two solutions. And once we have the two solutions, we make them into a single solution. Very, very easy. And then that you can also see that the characteristics equation has reduced the partial differential equation into an ordinary differential equation. And from this very point, you can make use of any method that you know for solving ODE to solve this, if it is applicable. So in doing that, we are going to look at our first equation. So with our first equation, we are going to pair any of these. So we have our first equation. So we are going to pair the x and then the y to find our first solution. So we have our dx all over xu is equal to dy all over yu. So looking at this, you realize that we have dx over x and then we have dy over u. So if you are able to massage this equation some more, we can separate the variables and then we integrate directly. So what do? What we are going to do is, if you multiply both sides of the equation by u, you can see that this u go away and then this u go away. You'll be left with what? The x over s and then dy over u. So we are just going to multiply both sides of the equation by what? U. So we have u multiplying dx all over what? Xu is equal to u multiplying dy all over what? Yu. So from here you can see that this u will cancel this u will also cancel what? This u. So we have our dx all over what? X is equal to what? Dy all over y. So from here you can see that we have separated the variables and therefore we can integrate to find our first solution. So we have dx all over x is equal to dy all over what? Y. So let's integrate with respect to x and then with respect to y. When we integrate the s over s, this one has become very common. So we don't have to think, we just have to say ln what? X. Then we add our constant of what? Integration. Since we haven't ln, let's take the ln of the constant at 12. So if we are going to have two equations, let's call this constant 1. And then when we integrate this, we are going to get ln and then y. Applying our basic knowledge in logarithm, we have ln and ln. We pick one of the ln, we multiply the arguments. So we are going to have what? X multiplying c1 is equal to what? Ln y. Now let's do away with the ln by multiplying both sides of the equation by the e. This will cancel this. This will cancel this. We are left with what? X multiplying c1 is equal to what? Y. We are interested in making C1 the subject or finding the constant C1. So you can say that our C1 is equal to what? Y all over X, and this becomes our first solution. So once we have this, we move on to the second equation. So with the second equation, what we are going to do is that we are going to pair the u with any of these fractions. We can either pair the u with the y or the u with what? The x. But realize that when we pair the u with the y, it will be very difficult for us to separate the variables and then integrate. And it will be very difficult for us to solve. Also, when we pair the u with the x, it will also be very difficult for us to separate the variable because we have x squared, y squared. We can't separate the variables from here. So it will be very difficult for us to solve it. In that case, then we have to apply another techniques in order for us to find our second solution. So what we are going to do is that we are going to make sure that the denominators are the same. If the denominators are the same, we can equate their numerators and then integrate directly. So what we are going to do is that we are going to multiply each fraction by a factor of 1. We are going to do what? Multiply each fraction by a factor of 1. So the x all over xu, we can multiply it by what? X all over what? X. This is a factor of 1 because x will cancel x, we have 1. And then with the y all over yu, we are also going to multiply it by what? Y all over what? Y. And then the u, we are also going to multiply it by a factor of 1, and that is what? U multiplying x squared plus what? Y squared. Very, very easy and then simple. So from here, we can say that we have x dx all over what? S squared u is equal to what? Y dy all over y squared u is equal to u du all over what? U multiplying s squared plus what? Y squared. So as I said earlier on, we are going to make sure that the denominators are the same. And once they are the same, we can equate their numerators and then we integrate from there. So from here, we are going to apply our basic knowledge in algebra. This concept, we'll be making use of it more often, so I think you are familiar with. I said that, or we said that when you have two fractions, 3 over 6, and then 1 over 2, since they are equal, we can what? Add the numerators and then the denominators. And this is equal to any of the fractions, so 3 over 6, and this is equal to what? 1 over 2. We'll be making use of this concept more often. So we are going to apply the same concept here. Since these are 3 fractions and then they are equal, we can apply this concept. We are going to add this to that and then we equate it to the third fraction. So we have our x dx plus what? Y dy all over what? X squared u plus y squared u is equal to what? U du all over what? U multiplying s squared plus what? Y squared. So as I said, we are going to make sure that the denominators are the same. So for this to be the same as that, let's factorize u out. So we have our x dx plus y dy all over. When we factor u out, we have s squared plus what? Y squared. And this is equal to u du all over u multiplying s squared plus what? Y squared. So from here, you can see that the denominators are the same. And when the denominators are the same, you can just equate their numerators. Because when we have a fraction, let's say 1 over 4, and this is equal to, let's say, y over 4. Since the denominators are the same, we can equate their numerators to have this. That is what we are going to do here. So we have x dx plus y dy is equal to u du. So from here we have separated the variables into x, y, and then u. So we can integrate term wise. So when we integrate x dx, we are getting x squared all over what? 2 plus when we integrate y dy, we are getting y squared all over 2. Then we add our constant of integration. So we have c2. Since we have c1, let's call this c2. And then this is giving us u squared all over 2. So let's clear the fractions, okay, by multiplying through by 2. So we have our x squared plus y squared plus 2c2 is equal to what? U squared. So let's make c2 the subject by sending the whole of this to the right hand side. So we have 2c2 is equal to u squared minus s squared minus what? Y squared. Now we have a constant multiplying a constant. It's still going to give us what? A constant. So we can write this as c2 is equal to u squared minus s squared minus what? Y squared. Very, very easy. And then simple. So we have our second solution as well, which is this one. Since we are having two solutions, we are going to merge them into a single solution. So one becomes a function of the other. Let's continue from here. Now we have our C1 and then C2. Since we are having the U in C2, let's make C2 a function of what? C1. So we have C2 to become a function of what? C1. Our C2 we had U squared minus what? S squared minus Y squared is equal to a function of C1. That is what? Y all over what? X. So from here, we want to make what? U the subject. So you can say that our U squared is equal to what? A function of y all over x. This is going to give us plus s squared. This is also giving us what? Y squared. Let's make u the subject, not u squared. So we have our general solution, which is in terms of x, and then y is giving us what? The square root of a function of y all over x plus s squared plus what? Y squared. Very, very easy and then simple. So this becomes our general solution. It becomes what? Our general solution. Now with the question, we realize that we are being given an initial condition with this. So you have to proceed to find our particular solution. We have to proceed to find our particular solution. So let's write our general solution. U at x, comma y is equal to the square root of now with the initial condition, we are saying that u at x, comma 1, right? So it means that wherever we see x in the general solution, we should plug in x, and then wherever we see y in the general solution, we plug in what? 1. So we have our u at x, our y is 1, so we have 1 is equal to the square root of, so we have our y is what? 1, so we have a function of 1 over what? X, and then we have plus, our x is still x, so we have x squared, and then our y, we have to plug in what? 1. 1 squared will give us what? 1. And then we have the initial condition, u at x, comma 1 is equal to what? The square root of what? S squared plus 1. So from here, what we are going to do is that, since we have u at x1, since this is equal to that, then we can equate this to that. Very, very easy and then simple. So we are going to say that our root of 1 all over x plus s squared plus 1 is equal to what? This s squared plus 1. So from here, you can decide to square both sides of the equation to cancel what? The radical sign. So we are left with a function at 1 over x plus x squared plus 1 is equal to what? X squared plus 1. So from here, we can decide to make this the subject. We have f at 1 over x is equal to this will give us what? 0. We have 0. So from here, what we are going to do is that we are going to let any variable at all, let's say p, to represent what is in the function. So we are letting p is equal to what? 1 over x. Then from that, we make what? X the subject. So you can say that our x is equal to what? 1 over what? P. So this means that wherever we see 1 over x in this equation, we are going to plug in p. And wherever we see x, we plug in 1 over p. So from here, we are going to get f at what? P is equal to what? 0. So at this point, what we are going to do is that we are going to go back to the general solution. We are going to do what? Go back to the general solution. So this is the general solution. And then wherever we see p, we are going to plug in what? Y over x. Wherever we see p, we are going to plug in what? Y over x. So we are going to have f at y over x is equal to what? Still 0. Now this means that wherever we see f at y over x in the general solution, we plug in what? 0. Wherever we see f at y over x in the general solution, we plug in what? 0. So if you plug in 0 here, we are going to have our particular solution to be u at x comma y is equal to the square root of this will give us 0, the whole of this will give us 0. So we are left with x squared plus y squared, and this becomes the particular solution. So this is what? Our particular solution. Let me write it here. Very, very easy and then simple. See you tomorrow. Bye bye.